Okay.
So last week we talked about compounds as a whole. We talked about compounds, not necessarily what makes a compound. Okay? We talked about ionic compounds, molecular compounds, the difference between them. What's the one thing you look at to differentiate the two? Metals. There's a metal, it's a what? Ionic. No metal is molecular. Okay? If it's molecular, you have prefixes. If it's ionic, you don't. Okay? Today we're going to look at what is a compound. We're going to go at the atomic and bond level. Okay? We haven't really talked about bonds yet. You've certainly heard of chemical bonds, but today we're going to actually talk about what a chemical bond is. Okay? So today, we not only have chemistry cat, there's also chemistry dog. Okay? Chemistry dog is not as big if you're a chemistry pet aficionado. Chemistry dog is not as big as chemistry cat. Okay? So chemistry cat is saying his name is ionic bond, it's taken, not shared, and chemistry dog is covalent bond, shared, not taken. Okay? So we're gonna keep coming back to that taken or shared. Okay, that's gonna be really, really important for us. So a bond as a whole is just a source of attraction which creates a force that holds two atoms together. Okay? It could be two atoms in an ionic compound. Remember we talked about the big crystal lattice, where you just have negative atoms and the positive atoms that are just kind of mixed together. Or you can also be in a molecule. In a molecule, you have a single molecule that's made up of a certain arrangement of atoms. Okay? But a bond, there are multiple types of bonds that we'll see, are what hold that structure together. Okay? There are ionic bonds and there are covalent bonds, and we'll talk about that quite a bit. Okay. In ionic compounds, just give me an example of an ionic compound. What's the most common one? NaCl, sodium chloride. That's an ionic compound. Okay. What is the charge of the sodium ions in NaCl? Plus one. What's the charge on the chloride ions? Minus one. Opposites attract, right? Pluses attract minuses. This is a plus, this is a minus. They're attracting, just like magnets. There's a force holding them together. Okay? That is an ionic bond. It's just the difference in charge that makes the two things attract. Covalent bonds, as we'll see, are held together by a sharing of an electron. They don't necessarily have charges that are holding them together. They're just both holding on to the same electron, and neither one wants to let go. So that is the force that's holding them together. So we talked about ionic bonds. All it is electrostatic. Okay? That means electricity. Plus attracts minus. Opposites attract. That's all it is. So here we have yellow atoms and green atoms. Let's say the green atoms are the positively charged ones, the yellow ones are the negatively charged ones. So they're arranged in our crystal lattice. The pluses are attracted to the minuses, right? All the green ones are attracted to the yellow ones. But the green ones are repelled from each other, and the yellow ones are repelled from each other. If you have two negatives, they want to go away from each other. Two positives want to go away from each other. Just like if you take those magnets and you flip one of them around, all of a sudden instead of being pulled together, you can actually feel them being pushed apart, right? So in our crystal lattice, we have all of that going on. And where the atoms settle in this crystal lattice is where all of the forces are at equilibrium, okay? Each atom is in its happy place, okay? It's not being pushed, it's not being pulled, it's just sitting in place. Okay? Remember, ionic bonds, because they form ionic compounds, always happen between a metal and a nonmetal. You will not have an ionic bond between, say, sodium and lithium or oxygen and fluorine. In an ionic compound, the electron is transferred from the cation to the anion. Remember, we talked about this quite a bit. Cations like to lose electrons to get to the noble gas configuration, right? Anions like to gain them. But cations don't just randomly lose them, and anions don't randomly gain them. The cations give them to the anion. Okay? So, we're going to use this later on. This is a shriveled up tangerine I found in my refrigerator. Okay? I don't like shriveled up tangerines. Okay? Let's going to say I am a cation. Is there anyone here that happens to like shriveled up old tangerines? Is there any? Okay. So Ben likes shriveled up old tangerines. Okay? So let's say I am sodium. I have one electron I want to get rid of. Okay? Ben is chlorine. He wants to gain one electron. So I'm just going to give him that electron. But it's my electron. I can't leave it. Okay? I'm letting him borrow it. But now I am positively charged, he's negatively charged, we're stuck together. I can't leave that electron. Okay? That is what an ionic bond does. You had multiple dried out tangerines, you could transfer two of them to Ben. Okay?
So they share it?
No, I gave it to him. I didn't want it, he wanted it, so I gave it to him. But since it's mine, I can't just walk away. Okay? I'm now positive, he's negative, so now there's a force holding us together. Okay? But I have no control of this electron anymore. I have given it to him. Or you could say he took it from me. The end result is the same. Okay? That's why Chemistry Cat was saying taken, not shared. He took it from me, we're not sharing it. And we'll see what sharing is in this bit. Ionic bonds are very, very strong. They are the strongest bonds you can have. Okay? Covalent bonds are bonds created by the sharing of electrons. So let's say I have a tangerine. I want half a tangerine. I don't have any way to cut it. Okay? And Ben wants half a tangerine, but we can't cut it. So I'm just going to hold it out, he's going to grab it, and we're both going to hold on to it. Okay? Now we're both happy. Okay? So we're just going to hang out in between us. We both can say this is our tangerine, but in reality we're sharing it. Okay? So that is a covalent bond. We're actually sharing it. We're both holding on to the same electron. This happens between two nonmetals. Okay? This is our molecular compounds, not our ionic compounds. The electron is not transferred. Okay? This is not something that makes a positive ion and a negative ion. We both more or less stay neutral. We'll go more in depth into that later on. But more or less, we both stay neutral. Okay? Usually, electrons get shared in pairs. Okay, and we'll see this. Say I had one tangerine and Ben had one tangerine. We both wanted two. Well, let's say this is another electron. This is one electron. This is one electron. Okay? I'm going to give this one to Ben. I have this one. We both want two. We each only have one. So if Ben holds on to this one, and I hold on to this one, we're now each sharing the one we had, so we both technically have two. So now we're both happy. Covalent bonds are weaker than ionic. By default, I said ionic are the strongest. Okay? Covalent bonds are weaker than ionic bonds. So, NaF, sodium fluoride. Would you say that is ionic bonding or covalent bonding that's holding the sodium with the fluorine? Why?
Two nonmetals.
Is sodium a nonmetal or a metal?
No, it's a nonmetal.
sodium is a metal, right? It's all the way to the left. So if sodium is a metal, is this ionic or covalent? Ionic. How about this? Covalent. Why? There's no metal. So it has to be covalent. How about this? Ionic. Because iron is a metal. How about this one? I heard a couple. Covalent. How about this one? Calcium's a metal. Actually, this one has both ionic and covalent. If I tell you that, why is there both ionic and covalent here? Right, there you go. The ClO2 in itself, in the, I believe that's the chlorite ion, there's covalent bonding holding the chlorine to the oxygen. That is a unit. Something's holding that unit together, and they're both nonmetals. So that is covalent bonding. But then there's ionic bonding between the calcium metal and the chloride anion. So you have covalent bonding.
That's the covalent right there.
This is covalent, but then this bound to this is ionic. Okay. Don't worry. There was one like this in the quiz, or actually, I guess in the homework. I took it out. So you don't have any that are both. Okay. So just be aware that something like this, you can have one and the other. They're not mutually exclusive. It all depends on how you look at it. Okay. Covalent can be polar or nonpolar. Okay. This is going to come down to strength between Ben and I. Who wants the shriveled up tangerine the most? Okay. So in polar covalent, there's an unequal sharing of electrons. Okay. So if I hold this out to Ben, right now it's in the middle. That's an equal sharing. If I say I want it more than you, it's closer to me, right? That is a polar covalent bond. Ben can also pull it closer to him. That is polar covalent also. Okay? Polar covalent bond always happens between different elements. And that's because different elements have different strengths. Okay? If Ben and I were the same element, we both have the same strength, tangerine would end up right in the middle between us. Okay? If we're different elements and one of us is going to be stronger, one of us is going to pull it closer to us. It's still being shared, but it's closer to either Ben or I. Okay? And then non-polar covalent, that's only when the atoms belong to the same element, or we'll see later on, the one exception is carbon and hydrogen. Carbon bonded to hydrogen is non-polar covalent. Okay? Any other combination of elements is automatically going to be polar covalent. Any two atoms of the same element bonded together is nonpolar, or carbon bonded to hydrogen is nonpolar. Okay. Let's find. Polar covalent bond is stronger than a non-polar covalent bond. Okay? A polar covalent bond is sort of halfway in between a pure covalent bond and an ionic bond. And the closer you are to an ionic bond, the stronger you become. Okay? We said ionic bonds are the strongest there are. So the more you are like an ionic bond, the stronger that bond is. Non-polar covalent bond is weaker than and a polar covalent bond. And we describe these polar bonds by talking about their polarity. Okay? A more polar bond has a more unequal sharing. So if I pull the electron really close to me, that's a very unequal sharing. Okay? That means that bond is more polar, which means it's stronger. Okay? So this is just a flow chart, really easy to classify your bond. Either you're ionic or you're covalent. If you're covalent, you're polar, you're non-polar. Okay.
So does that mean like as you move up the chart, the ones with the smaller radius are gonna have the,
We'll talk about how to determine which one's stronger.
yeah.
Yeah, we'll talk about that. Okay. Because the electrons are not shared equally, what we get are partial charges. Okay? And that is what this delta, this is a lowercase Greek delta. Okay? When we say delta minus or delta plus, that means a partial charge. So in sodium chloride, the sodium has a full +1 charge, the chlorine has a full -1 charge. In FH, neither one is a metal. Okay, so it's covalent, but as we'll see, fluorine is very, very, very strong. So it pulls an electron very close to it. So if it has more or less pulled the electron from hydrogen to it, they're both sharing it, but it's right next to fluorine. What charge does this electron have? What charge does an electron have?
Negative.
Minus, right? So if I started, say, how many valence electrons does fluorine have to start with? 7. It wants to get to 8, right? If it got to 8, what charge would fluorine have? -1, because it went from 7, that point it went to 8, so that's -1. If I'm sharing this with someone, but it's basically mine, I'm almost to 8, but not quite. Okay? So I don't have a full -1 charge. I have a partial negative charge. Okay? So whatever atom the electron is closest to has the partial negative. The one that's further away from has the partial positive. Electronegativity is that strength. Okay? We measure the strength, the ability of something to pull on an electron is electronegativity. If you have a difference in electronegativity, you get a polar covalent bond, which is more like an ionic bond, and so you have increased bond strength. You have a stronger bond. So, did you get it?
You guys good?
So the further apart the strengths of the two atoms are, the more like an ionic bond, the stronger it is. If you have no difference in electronegativity, you have a non-polar covalent bond. So, as we'll see, the only way to have no difference in electronegativity is to either have two of the same atom, two of the same element, or carbon and hydrogen. Okay? We measure electronegativity on a scale. Okay? It doesn't have units, but there are numbers involved. The higher the number assigned to that element's electronegativity, the stronger it is. And the higher the electronegativity, the stronger it pulls, the closer it pulls the electron to it. So the one with the higher electronegativity gets a partial negative because it's almost gaining an electron. The one that's weaker gets a partial positive because it's almost losing an electron. So this is the electronegativity scale. The thing to remember is fluorine is the highest. The top right corner is the highest. So if the top right corner is the highest, as you go to the right, you get higher or lower?
But is it go higher?
Higher. If fluorine is the highest, okay? As you go to the right,
Oh,
you get higher.
yeah.
Thank you. If fluorine is the highest, as you go up, does it get higher or lower?
Higher.
Higher, okay? You'll notice there are elements missing here, okay? Helium, neon, and argon are missing. They are so unreactive, they don't even have electronegativities, okay? So we say fluorine is the highest, top right corner is the highest, even though fluorine isn't in the top right corner of the periodic table, it's in the top right corner of this, okay? I would not give you a question asking you which has the higher electronegativity, fluorine or helium, okay? If you can remember fluorine is the highest, top right corner is the highest, you'll be fine. So, like I mentioned, there's a number assigned to each element. There are no units. What you can do is you can take, say you have a bond between sodium and chlorine, okay? What is the difference between the chlorine and the sodium? In the number. How would you find the difference? You subtract. 3.2 minus 0.9 is 2.3, okay? So the electronegativity difference there is 2.3. What if you have a bond between sodium and bromine? What's the difference there? 2.1. So which one is the stronger bond? Why bromine?
Just to the right.
Remember, why bromine? Why chloride?
Because it has a larger difference.
Right.
It's pulling much harder.
Right. The larger the difference, the stronger the bond, the more like an ionic bond you have. Because with sodium chloride, that chlorine is pulling on the electron harder than the bromine does. Okay? So it gets it closer to it, so that partial positive and that partial negative become stronger. The larger the difference in electronegativity, the stronger your bond. Yeah.
So if you go up to the right, makes it like stronger. Then how come the middle row of the metals in the middle are higher than like zinc or copper? It's like they're like 2.2, 2.3, but higher to the right is like 1.7, 1.6.
Like you caught, it's not a perfect fit. Okay. In general, you wouldn't be comparing, I'm guessing ruthenium to gallium. Okay, that's really hard. But if I tell you sodium and oxygen, that's easy. Okay, or francium and sulfur, you would have something like that. Or chlorine and bromine, or oxygen and nitrogen, something like that. They'll either be so far apart that it's obvious, or they'll be right next to each other. So here we have to figure out whether they have polar bonds, and if it's polar, which one has the partial negative. So the bonds between sulfur and oxygen in SO2, polar or non-polar? Polar, why?
Because they're not the same.
Because they're not the same. Which one has the partial negative? Why?
It's closer to what?
Right. So here's oxygen, here's sulfur. We said as you go up, electronegativity gets higher. So, wait, what did we say sulfur or oxygen? Oxygen, okay, yes. So the oxygen is stronger. So it pulls the electron closer to it. If it more or less gains an electron, it becomes negative. Okay? How about N2? Polar or non-polar? Non-polar. They're the same. So if you go back, you take nitrogen, the difference between them is 0. If you have a 0, you're non-polar. How about H2S?
Polar.
Polar.
Sulfur.
Right. So it's polar because they're not the same and they're not carbon-hydrogen. And sulfur is higher electronegativity than hydrogen. How about CCl4, polar, non-polar? Polar, which one is strong? Which one has a negative charge? The chlorine. Chlorine is right under fluorine, the carbon is several over. And O3, how about that? Non-polar. Everybody know what O3 is? Ozone. O3 is ozone. Okay. So that is our covalent bonds. The covalent bonds are much more complex than the ionic. Okay? Because you can have polar, you can have non-polar, you have increased ionic character, you can have strong ionic bonds, strong covalent bonds, weaker covalent bonds, things like that. The ionics are a little more straightforward. Metals, like we said, lose electrons, become cations, and non-metals gain electrons, become anions. That's nothing new. We talked about that last week or the week before that. Okay? And we said, we already talked about why that happens. They want to become like a noble gas. Right? This is nothing new. So, when we mix sodium and chlorine, sodium metal and chlorine gas, the electrons actually get transferred from the chlorine gas to the sodium metal. And when that happens, you get sodium chloride. It talks about the attraction and repelling forces. Why do you think ionic compounds are hard and brittle? Let's start with hard. That one's a little easier. What do you think would make something hard, difficult to break apart? Strong bonds, right? The stronger the bonds in something are, the harder it is to pull it apart, the harder it is to break. Ionic bonds are the strongest bonds, so ionic compounds are the strongest compounds. Okay? And brittle is not straightforward. I'll give you just a couple seconds. If anybody sees something, what?
Yeah, because they're in a regular shape, it's a lot easier to hit it at certain angles and put apart.
Exactly. So, in an ionic compound, it's in this regular pattern. Okay? If you take a pick and you put it right here, what's going to happen is it's going to split right down this line. And when it splits down that line, all the ionic charges remain the same. If you got just a random crack, in one piece you may have more negatives, in the other one you may have more positives. That's why if you look at your salt cubes in your salt shaker, there's little tiny cubes, right? Because they had to break that way in order to keep an equal representation of the positive and the negative in each piece. Why do you think ionic compounds don't conduct electricity when they're solid? We talked about, I think last week, what has to happen for something to conduct electricity, which we're talking about electrolytes, non-electrolytes. Sorry?
A metal.
You have to have a metal, yes? They have to be soluble. What does being soluble let you do?
Does the electron have to move?
The charges have to move. So in electricity, electrons are moving. In ionic compounds, the ions are moving. So if you have salt water, remember the sodium ions and the chlorine ions are separate. They can move around. If you have sodium chloride solid, the ions can't move. If the ions can't move, the charge can't move, which means it won't conduct electricity. We talked about that. So in CO2, there are covalent bonds, and then later on we'll talk about intermolecular forces. Okay. in CO2, you have strong bonds. They're much stronger than the forces that are holding one CO2 molecule to the other. So when CO2 sublimates, remember that's going from solid to a gas, CO2 molecules one at a time will come off. They don't break apart, they just come apart from the other molecules and float away. Each molecule is completely independent. Okay? If I go back to the ionic, these atoms are not independent of each other. Okay? They are all in a unit. Okay? The positive ion has to have a negative ion to go with it. That sodium ion can't just decide to float away. In a covalent compound, every single molecule is its own thing. If you have a cup of water, all the water molecules in there are acting independently from each other. Okay. Now we get to do Lewis structures. Okay. Before we did Lewis dot symbols. I told you not to worry about it too much because we're going to come back to it in a big way, in a much more difficult way. Okay? That is not.
I don't remember exactly discussed like that, but.
More or less. I have it on video. I can find it. So, what you need to do, and we're going to start easy and get harder. Okay? It's basically a puzzle. It's really just a puzzle. What it's going to be is you're going to arrange atoms, and you're going to have to put your little dots for electrons so that all the atoms are happy. That's basically what it's going to be. A puzzle to make all the atoms happy at the same time. Okay? In a covalent compound, which is what we're going to use these Lewis dot structures for, every atom has to be in noble gas configuration, which means 8 valence electrons. Okay? We only deal with valence electrons here. Okay? So, because everything has to have 8, we call that the octet rule. Every atom has to have 8. There is one exception, hydrogen. Yes?
Isn't helium the same way?
Helium is the same way, but because it's a noble gas, it doesn't form compounds, so we never use it there. Yes. But hydrogen is everywhere, okay? You'll use hydrogen a lot. Remember, hydrogen only gets 2, not 8. Everything except hydrogen gets 8. The only exception is hydrogen, which gets 2. Okay? So this is CF4. If you look, every atom has 8 dots around it. The carbon has these, each fluorine has 8 around it. These are shared between a carbon and a fluorine. They can both count them. They don't care that they're shared. Okay? So the carbon is sharing all 8, but it's perfectly happy because it has 8. The fluorines each share 2, but they're perfectly happy also because they have 8. Here is fluorine and hydrogen. Hydrogen only wants 2. So hydrogen has 2, fluorine has 8. They're both happy. It says 8 electrons. Don't forget 8 electrons. And the 8 electrons will always, always, always exist in 4 pairs. We never, ever move around single electrons. Okay? Pairs move as a pair. Okay? A hydrogen atom will always have 1 pair of electrons between it and another compound. Hydrogens are the easy ones. Because hydrogens can only have 2 electrons, which is 1 shared pair. Other atoms we'll find can have single, double, or triple bonds, depending on whether they have 1, 2, or 3 shared pairs. So hydrogens on a structure are gimmies. You'll write hydrogen and put 1 pair of dots between it and the atom it's bound to. Okay. easiest one is diatomic elements. Okay? What are, looking up here, which ones are the diatomic elements?
Same period as.
Right. So you have nitrogen, oxygen, fluorine, and then the halogens, and hydrogen over here. Okay. Hydrogen is the simplest one because that's all there is to it. Okay. So what we're going to do is we're going to write hydrogen and hydrogen. We know hydrogen exists at H2. Okay. So we have one hydrogen and one. First thing we do is we add up how many valence electrons we have to work with. Okay? So how many valence electrons does each of these hydrogens bring? One. So we have a total of 2. The way I do it is I write out the structure, and then above I write how many electrons I have to work with. Okay? And then the key is to use that many electrons to make everything happy. This one, there's a couple ways you can come at it. One is you can say, well, there's only 2. Each hydrogen has to have 2. So there's only one place I can put that pair that's going to make them both happy, which is where?
In the middle.
Between them. I can do it like that, and they're both happy. The other way to think about it is to say, automatically, if I have a hydrogen bound to something else, there's 2 dots. So I automatically put those 2 dots there, and then I look at, okay, how many do I have? Well, I already used them all, so I'm done. Okay? Let's look at another one. How about chlorine and chlorine? How many valence electrons each chlorine brings? 7. So how many do we have total? 14. So we're going to put 14 here. The first step, if you have a bond, is to put the first pair there. Okay? And then we're going to start on the outside and fill around here. Do that until we've used up all 14, and then stop and see if we have to rearrange anything. So there's 2. I'm going to go 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's my 14. Is everything happy?
Yes.
Yes. This chlorine has 8. This chlorine has 8. Does everybody see that? Another way to see this happening is to draw them separately with their electrons first. So they each have 7, right? So if I go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, you can see that if you slide these together, that one's going to pair with that one to make a pair, right? Can you see that visually? This isn't going to happen all that often, okay, where you see it like that. This is the way you're going to have to do it, okay? Where you put one dot to make a bond between everything, you fill it all in, and then see if you have to change anything. And we'll see plenty of examples. There's going to be a bunch of them. Because this, like I said, it's a puzzle. So the more puzzles that you do, the quicker it becomes, the easier it becomes, right? The concept isn't all that hard. Arrange the dots so that everything other than hydrogen has 8, hydrogens have 2. It doesn't take a rocket scientist to understand that. Where it gets tricky is doing it. Okay? So the only way to do that is practice. Okay? These are the diatomic molecules, just like the chlorine that we did. Okay? These are all halogens. They all have 7 valence electrons. So they all pair just like our chlorine did. How many valence electrons does an oxygen atom have?
6.
6. 1, 2, 3, 4, 5, 6. How many does it need to gain to get an octet?
2.
2. Okay? If you have O2, oxygen bond to oxygen. Can you do that with a single bond? So, if we put, let's just do it in order. If we take our oxygen, and our oxygen, how many total electrons do we have to work with?
12.
12. I'm gonna write 12 here. First thing you do is you put one pair between your atoms, okay? So there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's my 12. Is everything happy?
No.
No. Okay. So, I can put that here. What if I take these and move them over here?
Nope.
Now is that fine?
No.
No. What if I split this pair and go like that?
Nope.
No. That breaks two rules. That has 7, that has 7, so the octet rule is not satisfied, and we also have single electrons, which I said we can't do, right? So there's only one way we can do this. What is that, do you think? A double bond. If they each share 4. Okay? And the way I would do this, if I was writing a structure, is I would do it just like we did, end up with that, and stop and say, is this happy? I would say, no, what can I do? Move those over here. Okay? I wouldn't look at that and immediately say I need a double bond. Okay? I would draw it out, see that it was wrong, and then figure out what can I move to make it right. Okay? So don't make it more difficult than it has to be. Take it step by step. So if we have these two pairs, we call that a double bond. Okay? There's double bond, single bond, and we'll see triple bond also. And there is our triple bond. Nitrogen bonded to nitrogen. How many valence electrons does nitrogen have?
5.
5. So if we have N2, how many valence electrons do we have? 10. So I'm going to write 10, N, N. Start with our first pair here. That's 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all I can work, that's all I have. That's not correct, right? Neither one's happy. So, if I move that here, I now have N double bonded to N. That pair is there, that pair, and that pair are still there. Is that correct?
No.
No. I also have to move this pair down to get N triple bonded to N, and then each nitrogen has its own pair there. So this nitrogen has 8, this nitrogen has 8. Everybody see that? Just a matter of moving the little dots around. For every electron an element wants, or sorry, atom wants to gain, it generally has to form one bond to get it. Okay? How many electrons does a hydrogen atom want to gain?
1.
It wants to end up with 2, it starts with 1, so it wants to gain 1. Hydrogen will always form one bond. Okay? Remember, it can only have one pair, so by default, you can only have one bond, right? How many does chlorine want to gain? 1. So a chlorine, or any of these halogens, are only ever going to form one bond. If you have a halogen with more than one bond, that's wrong. Even if it's a double bond, it's wrong. If it's 2 single bonds, it's wrong. Yeah.
How do we know that they want to form one bond?
How many electrons does a halogen want to gain to get it to be a noble gas?
Oh, so it's all about getting to a noble gas.
Right. So you can think about it the same way as the charges. What charge would a halogen form? Anybody? -1. So if you take that 1, it wants to gain 1. So it's going to form one bond. Okay? What about oxygen?
what charge when oxygen forms?
2.
2 minus, so it wants to gain 2, so it forms 2 bonds. That can either be 1 double bond or 2 single bonds. Okay? Nitrogen would form what charge?
Negative.
3 minus, so it wants to gain 3, so it's going to form 3 bonds, which is exactly what we saw here, right? And carbon, 4. It has to gain 4, so it's going to gain 4 bonds. Okay.
So this is just an easier way of.
Well, it's a way of checking your work.
Okay.
Okay, so you get to the end, even if everything is happy, you may see, oh, but I have this chlorine that has 2 bonds, so something is wrong. Okay. These are just in words what I was telling you. Write your atoms. So far we've only had 2, so that's easy. It'll get harder. Write what we call your skeleton, just your atoms, rearrange them. Put a number of total valence electrons we have to work with above it. Put 1 bond between each pair of atoms. If you know they're bonded together, just put 1 pair to start with. And then start adding them to the outside until you run out, and then move them in to make everything happen. Okay. So here's our first one that has more than 2. We have formaldehyde, CH2O. Okay. Generally, and if you have this on a quiz or something where you question what the skeleton is supposed to look like, ask me. Okay. Generally, the thing in the middle is going to be the first thing listed. It's usually going to be carbon or phosphorus or nitrogen or sulfur. It's not going to be a halogen, it's not going to be oxygen, it's not going to be hydrogen. Okay? Generally, you have something other than those in the center, and then oxygen, hydrogen, and halogens around the outside. Okay? So, here, our carbon is in the middle. So I'm going to write carbon here, and we have two hydrogens and an oxygen bound to it. Okay? So if we were going to have 4 things, we would just put 1, 2, 3, 4. Okay? So we only have 3. There is no correct way to do it. Just make sure you have the 4 sides. Don't put 1 here, 1 here, 1 here. Okay? Keep it in quarters, but leave one of them blank. So I'm going to put a hydrogen here, and an oxygen here. It doesn't matter where you put those. It'd be just fine. Okay? So here's our skeleton. How many valence electrons do we have to work with? How many does the carbon bring? 4. How many does each hydrogen bring? 1. And there's 2 of them. So now we're up to 6. How many does the oxygen bring? 6. So how many do we have total? 12. So total is 12. First thing to do is put our single bonds in. There's 6 of them. Okay? Now we start on the outside. The hydrogens are already happy. They already have their 2. So I can't add anything more to them. Which means the rest of them have to go on the oxygen. Okay? So there's 6. I'll go 7, 8, 9, 10, 11, 12. There's my 12. So I step back and say, is that correct?
No.
No. Why not?
Because
Because
carbon needs
it's-
2 more electrons.
Right. Carbon only has 3 at this moment. How can I give it 4?
Double them up.
Involve the oxygen.
Right. I can pull, it doesn't matter where I draw the arrow from. I can pull 1 pair up to there, which gives me carbon, hydrogen, oxygen, 1, 2, 3, 4, with a double bond here. And now I have it like that. Okay. I wouldn't, if you drew it like that, I wouldn't care. Just don't split up a pair. Don't put one here, one there. Keep the pair together. Okay? So now, is everything happy? Yes. And we can check it. Hydrogens have 2. Carbon has 8. Oxygen has 8. We can also look at the number of bonds. How many bonds does carbon want to form? 4. Did it form 4? Yes. How many bonds does oxygen want to form? 2. Oxygen is here. It's a 2 minus, so it wants to gain 2, so it forms 2 bonds. Did it form 2? Yes. It formed 1 double bond, which is equal to 2 single bonds. Yeah.
Would the element furthest away from being a noble gas be the one in the middle always? We need more bonds.
No. Because you can, just in my head I'm picturing, you can have PO4. So the oxygen's closer, but the oxygen's right outside. You're pretty safe saying hydrogens, oxygens, and halogens are going to be on the outside. I can't think of an example, maybe we'll see one. I can't think of an example where you have something on the outside that is not an oxygen, a hydrogen, or
I'm
a halogen.
saying like would that one be in the center? So like the further away it was, be in the center. So like, would like aluminum be in the center as opposed to like phosphorus? This needs more bonds.
That's a good way of thinking, yeah. If you're on the outside, you're kind of limited to how many bonds you can form. If you're in the middle, you now have all these options of everything around you to form bonds with. That's a good way of thinking of it.
Do we have to draw the circles on it, or can we leave it like that?
No, you don't need to draw circles, no. So if you were asked a quiz or something, Lewis structure for formaldehyde, it would be exactly like that. So these are the steps. If you need to go back to and look at them, fine, that's exactly what we did. So here is hydrogen cyanide. You've all heard of cyanide, right? What is cyanide?
So that's deadly.
Very deadly. Basically, it's the little spy suicide pills. That's hydrogen cyanide. So, we are going to make the Lewis formula for hydrogen cyanide. So, in this case, the first one is not the one in the center, okay? How do you know that?
This is hydrogen.
It's hydrogen. Hydrogen's going to be on the outside. So, in this case, it is written in the order that we're going to write it, okay? If you saw this on the quiz, ask in your question, you're questioning what the structure is, ask me, okay? So I'm going to write HCN. Yes, and carbon is further away from the noble gas. Carbon is in the middle. Okay. How many valence electrons do I have total?
10.
So carbon brings 4, hydrogen brings 1, that's 5, and then nitrogen brings 5, that's 10. Just add them up. We have 10, put our 4 easy ones in. Hydrogen's already happy. I'm done with hydrogen. Now I come to the nitrogen on the outside. That's 4, 5, 6, 7, 8, 9, 10. There's my 10. Am I done?
No.
No. What do I need to do?
Form
Make
a triple
carbon.
bond with nitrogen and carbon.
Right. Carbon only has 4. It needs to gain 2 more pairs.
So
The only
double-
place it can come from is that nitrogen. So I'm going to take these, put them here, take these, put them here, and you get. So now hydrogen has 2, carbon has 8, nitrogen has 8, carbon has 1, 2, 3, 4 bonds, nitrogen has 1, 2, 3 bonds. So I'm just checking my work. Okay? So that is the correct structure for hydrogen cyanide. Step by step again. Here are a bunch of So CO2, what do you think is in the center? Carbon. So I'm gonna put carbon, oxygen, oxygen. How many electrons do I have? 16. Everybody see 16? You have, the way I do the math in my head, I do, oxygen has 6 each. There's 2 of them, that's 12. Carbon brings 4, that's 16. However you want to do that math, that's up to you. That's how it makes the most sense in my head.
Say it again?
I say, there's 2 oxygens.
Uh-huh.
Each oxygen brings 6. Do you see that?
Yeah.
Okay. So then that's 12, right? Carbon brings 4. 4 plus 12 is 16. So I have 16. I put my 4 easy ones in. Start on the outside. That's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is everything happy? No. What do I need to do?
Bring
two
carbon.
oxygen to carbon.
Right. So, carbon needs to gain 2. Okay? What would happen if I took that and like that?
The other oxygen still wouldn't be happy.
The other oxygen's not, oh, this oxygen is happy, it already has 8.
Wait, you said if you take one from each one?
Yeah, no, if I took, instead of forming a double bond here, double bond here, what if I formed a triple bond here? Right, oxygen can only form 2 bonds, so I can't do that.
Okay.
If I did that, everything would be happy with number of electrons, but oxygen would not be happy because it would then have 3 bonds. Carbon would be just fine, because it would have its 4, but this oxygen wouldn't be happy. So I need oxygen, carbon, oxygen, a double bond between each of them, and then each oxygen has 2 extra pairs. Now everything is happy. Okay. So let's go to a really closely related one, SO2. What's in the middle? Sulfur. Okay. S, O, and O. How many electrons do I have now? 18. Okay. Got 12 from the oxygens plus 6 from the sulfur is 18. Right, now I have 18. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I filled the outside, but I still had extra ones to give away. So now I can come in and start putting them on the inside. Okay? So there's my 18. Is everything happy?
No.
What's not happy?
Sulfur.
Because they're only one bond.
Sulfur's not happy.
No.
We need to take 2 from the oxygen and put it between the sulfur and the oxygen to make them all happy.
I heard a bunch of things I didn't understand.
We have to
All
take
happy.
2.
Yeah, everything's happy.
No, it's
All
not.
happy.
You gotta take 2 to give a double bond to oxygen.
This sulfur only has 6 electrons.
Needs
Yeah.
8.
Right. That, to me, that's the first thing that jumps out.
Yeah.
The sulfur, everything has to have 8. Okay? And that sulfur does not. So, how can I do that?
You can take 2 from the oxygen and put it with the sulfur.
If I take these 2, put them here, I now have that.
You're forgetting the 2 on the top of the sulfur. There, now it's happy.
But I thought sulfur only had 6.
Or do you take the 2 electrons off the sulfur and like move on to like the left side with the oxygen?
If I took B
Like
and
goes
put
in
here,
from there, yeah. Wouldn't that make it happy?
then this oxygen would then have 10. So, you're not going to perfect this, okay?
So oxygen.
This is as close as you're going to get, okay? What happens, and we're not going to deal with this, it's something called resonance, okay? What happens is this double bond is going to flip back and forth and back and forth and back and forth to try to make both oxygens happy. happy as you can be. Okay, you won't have a quiz question or anything like that. Resonance is a whole other area, okay? You can say, write a Lewis structure and write all the possible resonance structures for it. And resonance structures also can have charges, which means things can have more or less than 8. Yeah.
So would that one have 2 resonant?
Yes. So you can have that,
You would have almost.
or you can have it like that. But at any given time,
For a second, I thought you were reaching.
double bond is only on one side. We can't make it any happier than that. So let's go to another one that's really similar, NO2. NO2 minus. That minus is going to be really important. So what's in the center?
And nitrogen.
N. You put my O's. How many electrons do I have?
17.
Why 17?
Oxygen has 6,
Oh, wait,
so that
you
makes
have
12.
18 because of the negative and minus.
And nitrogen has 5.
So
Oxygen
you would have
has 6,
17
and you
normally
have
if
2
there was a negative
oxygens.
there, but
Right.
a negative would be 18.
So you have 12 from the oxygen,
Mm-hmm.
plus 5 from nitrogen is 17,
Mm-hmm.
plus 1 because it's negative charge.
Oh.
Okay?
So how many electrons are there?
So that means there's 18.
It has a negative electron.
You can't forget that charge.
It has
You
a
could have
negative.
something that has a positive charge, which means you have to add it up and subtract 1. Okay? NO2 minus, we're going to be at 18. Okay? So, there's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It looks pretty much the same exact thing, doesn't it?
Yeah.
So, we already know what the solution is. What is it?
Double bond or oxygen.
We need to make 1 double bond, and then the last thing you have to do to make this correct is you have to put the whole thing in brackets and say it has a negative charge.
So when it has a negative charge, it has to be in brackets with the negative charge on the outside.
Right. Or if it has a positive charge, put it in brackets and put the positive charge.
And if there's no charge, it's just neutral?
Yeah, if there's a positive charge,
Right.
you put the positive. If it's neutral, you don't need the brackets.
Okay, so the ones that we've been working with have just been neutral charges.
Right.
Okay.
Yeah.
So we're not gonna have that on the quiz.
I can't guarantee that.
Okay, so
So on this slide, this one's wrong again,
it's still resonant, isn't it?
What does it?
because it's showing the 16 instead of 18.
Isn't that on both of them? Yeah,
Is it 16?
Yeah, see, it's just cut off, so like we should just scratch it from the.
Yeah, because that oxygen only has 3.
That's the one that we're doing on right
Yeah. Do your slides have these?
Yeah.
Okay, so add those bottom dots. Okay. Dot, 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 dot.
That one's 16 electrons.
So are the slides are wrong?
The slides are wrong.
Okay.
Yes.
Okay, so
Yeah.
It has 18 valence, 18 electrons.
Right.
It's on, I thought it has 5 valence.
So there's 2 oxygens, 6 each, that's 12. Plus 5. Plus 5 is 17. Then it has a negative charge, so it has 1 extra to give it 18. Okay. Thank you for catching that. Yeah, it's on your slides. I never remember, because I go through and I delete some of the answers. And I never, by the time I get up here, I never remember which ones I deleted on your slides. So, in this case, this is more complicated than you're going to have, okay? Because, see this hydrogen here? It's not bonded to the center one. You're only going to have things where you have a center and the things around it, okay? But we can still do this. So there's our N, O, O, O. Now I have to put the hydrogen somewhere.
It can go on the outside of any of the O's, or does it necessarily have to be on the left?
It can go on outside of any of them. But why can I not put it here?
Because
Nitrogen can only have 3. It's already got 3. Okay? So, it can't go there. I know I can go on a oxygen, because oxygens can form 2 bonds, right? So if it forms a single bond with a hydrogen, and then it forms a single bond with a nitrogen, that oxygen is happy with bonds. Yeah.
Isn't nitrogen in that one forming 4 bonds though? Because it has 2 with the 1 oxygen.
what was
Yes.
the question?
So it's not right. It's because it's
It's gonna be that's gonna be the happiest it can be when we get there. Yeah.
The number of bonds the element wants to make, is that determined by how many valence electrons it wants to gain?
Yes.
So for instance, oxygen we want 2, and that's why nitrogen wants 3, and so
Right.
on.
Right, and as Matthew was pointing out, in this case, nitrogen is forming 4, so it's not really happy, it's the happiest it's going to get.
Okay.
So we'll do our singles. So there is, how many do we have?
24, I think.
18 plus 6 is 24. Okay. It's 24. So there's 2, 4, 6, 8. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's 24. Okay?
But nitrogen needs 8.
Right. So nitrogen
So we have
only
4.
has 6. The only possible way that it can get 8 is to
Take one from that top oxygen.
Yeah, it doesn't matter which oxygen, this can't be this oxygen. Either of these two, we can take it down. That's not
And it can't be that oxygen because of the nitrogen. I mean, not the nitrogen, but the hydrogen, right?
right. This oxygen already has formed 2 bonds.
Okay.
Yeah.
So would an element rather have a valence, like all 8 electrons and have the number of bonds it wants?
Yes. So it would much prefer having 8 electrons than being happy with the number of bonds. Okay.
Okay, and we couldn't take it and put it on the bottom because it wouldn't be connected to the oxygen then, right?
This pair, you're saying if you took that pair and put it here,
Yeah, it would
Yeah.
be
so
connected.
then nitrogen would have 8, but the oxygen would now have only 6.
Gotcha.
Yeah.
Is it only willing to do this in the case of double bonds?
I can't think of a situation where it'd be triple bond, but it would apply to that also.
But it won't do this for single bonds?
Here's an example. This may be coming up on the slide, I don't know. But, what if I do the ammonium ion? Okay? What's in the center?
Nitrogen.
Nitrogen. Where do those 4 hydrogens have to go?
Around the
Around.
nitrogen.
All around. So this nitrogen has to form 4 single bonds.
Don't forget the brackets
Thank you.
and the charge.
Yeah, so it would be 3 hydrogen, 4 hydrogen minus 1 plus the 5 nitrogen.
Nitrogen brought 2, 3,
Yeah,
4,
so it's
5.
That's minus.
I know I said it all the time and stuff. but-
Yeah. Yeah. So you would get 9,
Yeah, no.
but it's plus, so it lost 1,
Yeah.
so you're at 8.
Gotcha.
Thank you.
So is that how it would look if it lost one?
Yep. Which is why you have NH3 ammonia, which is happy with no charge. But when you add that 4th one, you now have 9 electrons and nowhere to put that 9th one, so it gets lost.
So is this kind of like breaking the rule of the triple bond?
This isn't breaking a rule of triple bond. Oh, it's breaking the rule of the 3 bonds.
Mhm.
Yes. It's breaking the rule of nitrogen having only 3 bonds.
So,
There's no other way.
but there's
The
no
hydrogen-
other way.
So that's the only exception, if there's no other way.
Right.
Makes sense.
Okay. This is, we're not gonna do organic chemistry, okay? But this is as close to organic chemistry as we're gonna get, okay? Organic chemistry is mostly carbon and hydrogen, okay? You can throw in some oxygen and stuff, but the most basic organic chemistry is carbon, hydrogen, okay? So this is C2H6, C2H4, C2H2. And what you're gonna see is as you lose hydrogen, something happens, okay? So C2H6, I'm going to tell you, you have C, C, and then there are 6 hydrogens. Where do you think they go?
Around.
3 on each one.
Yeah. Okay. How many electrons do I have?
6 plus
18,
6 plus
18.
6 plus 8, so
14.
14, right? Each carbon brings 4, that's 8, plus 6 is 14. There's 14. 14. Put the easy ones in, there's a bunch of them now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So with 14, is everything happy?
No,
No,
Why
because
not?
carbon only has 7.
the bombs.
Wait, yeah, it is happy because they're
That's
sharing the
fine.
2 in the middle.
Yeah, so each hydrogen has 2 electrons,
Mhm.
each carbon has 8, because they're sharing that. Each carbon has 1, 2, 3, 4, 1, 2, 3, 4 bonds. Happy as can be. Right?
So if you like increase hydrogens, would all the bonds increase?
Let's do it. The next thing is C2H4. So let's say we erase these, okay? How many electrons do I have? C2H4. 12. How many electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There.
Double
Double in
between
the
the
middle.
C's.
Right. So you remove 2 hydrogens, we gained a bond in the center. Okay? Next one is C2H2. What if I erase these? Now how many electrons do I have? 10. There's 1, 2, 3, 4, 5, 6, 7, 8.
This is one more in the middle.
One more in the middle. Triple bond. Okay. You see what I mean? It's not difficult, it's just a puzzle. You just do it,
brain teaser.
right? It's a brain teaser. It's exactly what it is. Just get your skeleton written, figure out how many electrons you got, and then figure out where to put them. That's all there is to it. Okay, there's some more. Somebody want to come up and do one of these? Ben, why don't you come up and do H2CO?
Hydrogen gives us 2, carbon gives us 4, and oxygen gives us 6, so we have a total of 12 values electrons.
12 electrons to work with.
Carbon is the furthest away from helium, so it'll go in our middle. Hydrogen, at least one going here. Oxygen is over there. That'll go far away, so there's on between that. Let's see. Oxygen starts with 6.
You got H.
The second hydrogen.
figure out where that goes.
And he's debating whether to put it on the carbon or on one of the, or on the oxygen.
Um, yeah, let's put you on the carbon and then double bond that. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is
Another one for
oxygen has
oxygen.
more electrons. That's how.
Makes sense? So he was able to see where things were going and did it more logically rather than stepwise. Where I would do it, put the single bonds in, do the outside and then move them in if you have to. He was able to see, I'm not gonna need to do that, I'm gonna need a double bond there, just put it in.
Could you put the hydrogen on the oxygen, or no, because it's got 2 bonds, that's why? Okay.
You wouldn't have enough electrons on the carbon in that way.
Well, I was thinking,
Yeah,
no, I.
your oxygen will also have them 3 bonds. Thank you. NF3, anyone? No?
I'll attempt.
You'll attempt? Thank you.
I'm probably gonna fail miserably, so don't learn from me.
I think this is gonna be a fairly straightforward one.
And I'm short, so I can't write anything either. So if you think about it, 5 times what, 7, right?
Yes.
7 times 3 would be 21. Nitrogen would be 5. 5 plus 21. 26, sorry. I'll eventually get my math right. Alright, so 26. So if you do N, probably have. So if we have.
Is she missing something?
No.
No.
That's it.
Did I do it right? Okay. I'll go confidently have a seat now.
So, I did note, you put the pair on the nitrogen before you finished fluorines. I would suggest, you ended up at the right place, so
Okay.
you're just fine. I think on some of the more complicated ones, you'll be doing yourself a favor by filling the outside
Fill in the outside
first.
before inside.
To me, it's easier to visualize taking it outside and making a double or triple bond than it is to realizing, well, the fluorine doesn't have one, but I have a lone pair here. What if I take it out there? Okay. In this case, it didn't happen, but in some cases, it will. H2O.
So oxygen brings 6, hydrogen brings 1, so that's 2. So you're gonna have 8 total. Oxygen in the middle, hydrogen, hydrogen. So that's 4. And then you want to double bond both hydrogens.
Don't double bond
No.
hydrogen.
In this case, all you have is hydrogen and oxygen, so one of them had to be in the middle. Hydrogen can't be in the middle because it can only form one bond. So oxygen was the only thing left. The oxygen in the middle is your single bond. You still have 4 left. Put them on the outside.
So let me understand, because I was a little confused on what goes in the middle. What goes in the middle is the one that can form the most bonds, and you want the ones that can form the least bonds on the outside?
In general,
Okay,
and that's a good way to start.
okay.
A good way to start.
I kind of feel like there's an exception here.
I'm sure there are, I'm just not, we haven't run across it yet.
Okay.
Lewis structures are just a pain in the neck. Or not, sorry, Lewis structures are a puzzle. Shapes are just a pain in the neck. Okay? It's going to become a long process. To figure out the shape of a molecule, you actually have to do the Lewis structure first, and then transform it into a shape, and then remember what the name of that shape is, and the angle of the bonds in that shape. Okay? But this is something you have to do. Okay? There's no way around it. Okay? Shape of molecules, to us in this class, isn't really going to matter, but the reason we study it is because biologically it makes a huge, huge, huge difference. Okay? You can have two chemicals that have the same exact atoms in them, but if they're arranged in just a slightly different shape, they can taste completely differently, they can smell completely differently. And I have an example of this. When I was an undergraduate, I was working in a chemical company part-time, okay? And we made cosmetics. Okay? One of the things we made were perfumes and colognes and things, okay? And my boss and I, neither one of us were cosmetic chemists. Okay? He was actually a theoretical physicist in charge of the cosmetics group. It was strange. And I was an undergraduate, okay? And so somebody told us we were supposed to make a perfume with a chemical called limonene in it. That name doesn't mean anything, okay? And so we ordered it. It came in and it had no smell. And we took it to somebody else and said, this doesn't have any smell. And he said, well, I smell it and it smells horrible. And so we emailed the people who wanted us to make it for them and said, why do you want this? Some people can't even smell it. Other people say it smells horrible. And it turns out that there are two different shapes of limonene. One has a bond that goes this way, one has a bond that goes that way. Okay? And that little difference changed it from either smelling nothing or smelling horrible to smelling nice. Okay? So we have the smell receptors in our taste bud and our taste buds, the taste receptors. It's like a lock and a key. Give us the right shape, it fits in, and it sends a signal to our brain saying, if something fits this lock, it must smell like this. Okay? So the shape of the molecule determines the taste and the smell. Okay? And also, with our enzymes, if you haven't taken biochemistry or anything like that, or biology, enzymes are what make life go. Okay? Enzymes do everything. They're proteins, they're functional proteins, they're not structural proteins. And the shape of that enzyme makes all the difference in the world. Okay? When you fry an egg or scramble an egg, all you're doing is changing the shape of the molecule, that protein. You're not changing it in any other way. But clearly, that egg that you start with, that could grow into a living thing, being changed into a scrambled egg, is a big, big difference. Right? So shape plays a huge role in biology. Okay? Sweet substances generally have a shape that's very similar to glucose. Okay? And that's glucose. Okay? The H's and the OH's are the kind of the key part of the molecule that fit into the sweet sensors on our tongue. So if you look at sweet things, they're going to look a lot like that. If you look at NutraSweet, okay, overall it looks absolutely nothing like glucose, but it has hydrogens and OHs in just the right places that it fits in the right lock the right way. So, I don't know what's going on. The cat is taking over. Okay. there is, this bullet is taken straight off the slides, okay? I didn't change it, but I added the cat, okay? This says there's a simple model used in Lewis structures allowing us to predict shapes of molecules. And like I told you, to me, this is anything but simple, which is why I added the cat, okay? Because the book, the slide says this is a very simple thing, right? 2 minutes and you're done, move on to the next thing. This, to me, this is probably the hardest conceptually in the entire semester. I mean, it's gonna vary from person to person, but to me, this is the hardest stuff to visualize on the molecular level, okay? It's called, in big, long term, valence shell electron pair repulsion therapy, VSEPR. A lot of people call it VESPR because it's very hard to pronounce that, okay? So people that kind of reverse the E in the S and call it VESPR, okay? The more correct way is called VSEPR theory, okay? If you break it down, it's going to make sense. We talked about if opposite charges attract, like charges repel, right? All electrons have what charge? Negative. Meaning, the electrons in an atom, around an atom, or in a molecule are going to get as far away from each other as they can, okay? And so, as the electrons move, the atoms are going to follow them. So the electrons are going to get as far away from each other as they can, and that is going to determine the shape of the molecule, okay? Which is why it's valence shell, because in our Lewis structure, we're only dealing with the valence electrons, right? But it's valence shell, electron pair, because electrons are always in pairs, repulsion theory. Repulsion, the pairs repel each other, and it's the theory that the repulsion of the electrons determine the shape of the molecule, okay? So that is where that big long thing came from, okay? Basically, it just boils down to the valence electrons want to get as far away from each other as possible. And you just have to do that, okay? The first step is to come up with what we call a parent structure, okay? And you get the parent structure by drawing the Lewis structure, okay? And then you're going to find your center atom and count the number of things attached to it. And a thing can be an electron pair that's not bound, it's not part of a bond, just a lone, we call it a lone pair, a single bond, a double bond, or a triple bond. Any of these things count as one thing. A triple bond is one thing. A pair of electrons that doesn't even form a bond is one thing. So you count how many things are around your central atom. Okay? Then the parent structure takes those things and maximizes the distance between them. Okay? This is where we come back to our shriveled up old tangerine. And we have marshmallows and toothpicks. So I basically just went around finding what I could come up with. Last semester it was a shriveled up old plum, toothpicks, and gummy bears. So we have our toothpicks. Our toothpicks are going to be our bonds. Our marshmallows are going to be our outer atoms, or our things. There are things. Okay. So if I have two things attached to my central atom, I'm going to put the first one here. Where is the second one going to go to get as far away as possible from this one? Opposite, right? So if you have two things, you have a shape like that. So they want to get as far away from each other as possible. Okay? Let's add a third thing. If I want to add a third thing, let's do it this way. Take this one out. Here's my first one. How can I add two more so that they're far away from each other as possible?
One by your thumb, one by your middle finger.
Would be like diagonal.
Right.
Like
So
floral.
basically like a peace sign, okay, or Mercedes, however you want to think of it.
Looks like a triangle.
So it's a triangle.
those are as far away from each other as possible, okay? 2 and 3 are easy to visualize. 4 is the hard one. If I want to add 4, how can I do that?
One on each side.
So if I put, say, 12, 3, 6, and 9 o'clock, that looks like they're as far away from each other as possible.
What about if you put one in the
No, I would
middle?
say that the top, the bottom, one where your thumb is, one where your forethumb is.
So you're saying,
Not that one. Okay, that's right.
so you're saying that.
Yep, it means the same thing.
No, same thing.
doesn't it?
The problem is, in 2 dimensions, that's as far away from each other as they can get, okay? But we're in 3 dimensions, okay? So you can actually kind of see it here. This is what we have to do. We take one that's going straight up, and then we kind of make a kind of a pyramid shape on the bottom. Okay? And when we do that, what we see is we can turn it, and if I put them in the exact right places, what you would see is that when I turn it, it always looks the same. One going up, and then a triangle going down. Okay? So that, if you have 4 things, that is what it looks like. Okay? It's in 3 dimensions. 2 and 3 things are 2 dimensions. When you add the 4, you have to go into 3rd dimension. Not completely dried out. Okay, so here is methane. Methane is CH4. How many things are around our carbon? 4. We have 4 single bonds, that's 4 things. So methane is shaped like that. Okay? When you have that shape, those bond angles are 109.5. You just have to memorize that. Unless you can think about that geometrically, which if you can, props to you. But otherwise, you just have to remember, if you are in this shape, that bond angle is 109 degrees. And every one of these, between every pair, is 109 degrees. Okay? I think there's a slide that shows all the bond angles, but if we go back to our 2, what's our bond angle? 180 degrees, right? If we go back to 3, what's our bond angle? 120. There's 360 all the way around, and there are 3 angles that have to add up, so that's 120 each. Okay. So those, if you forget on an exam, you can kind of think and figure it out. This 109, good luck. I'll remember it. Okay. Yeah. So here are our 3 parent structures. Okay. If there are 2 things, it is linear. It's 180 degrees. You need to know that these names also. It's linear. We have 2 things, it's linear, 180 degrees. If there are 3 things, it's called trigonal planar, it's 120 degrees. It's called trigonal planar, the trigon, I'm drawing a blank on the 3-sided shape. Triangle. Like a triangle, okay? I mean, it's called planar because they're all in the same plane. You see that? They're all in, we call this the plane. If we have one going up, these 2 are not in the same plane as that, okay? So these are all in the same plane, so it's trigonal planar. If you have 4 things, we call it tetrahedral. Tetrafourhedral, I don't know. Yeah. It's tetrahedral. Okay? You have to remember the name tetrahedral. Tetrahedral is going to come up all over the place. You have to remember tetrahedral, and the tetrahedral atom has 109.5 degree bond angles. Okay? Like I mentioned, first step, you have to draw the Lewis structure. So, our question here is determine the parent structure and bond angles for these. So NH3, the very, very first thing we have to do is draw the Lewis structure. Okay? So a molecular shape question is also a Lewis dot structure question. Okay? So let's do our ammonia. There are 5, 7, 8 electrons. 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There is our Lewis dot structure. How many things are on that nitrogen? 4. 4. 3 single bonds and a lone pair. Okay? They all count the same. So there are 4. What is the parent structure of ammonia? Tetrahedral. And what are the bond angles? 109.5. Okay? You may see in the book, I don't know if it's in there or not, that if you have tetrahedral, in one of them there's a lone pair and not a bond, that it kind of repels these stronger and the bond angle is less than 109.5. Technically that is correct. Some of the other professors here make their students know that and think that, okay? Instead of making you remember that, if it comes up on the final, I will tell them, okay, actually, I will tell them that I did not make you learn that, okay? So when we haven't talked about the final yet, but the final is multiple choice and written portion. On the written portion, I'm not allowed to grade yours, okay? Because they look at your score as a bit of a measurement of my teaching. So they don't want me grading your exams, okay? So one of the other chemistry professors will grade it. So then I will tell them, I didn't make you say it's less than 109.5, okay? If you see it in the book, don't worry about it. If you talk to somebody else who's taking it in, say, Dr. Owusu's class, they may think you're slow because you're just saying it's 109.5, but you can tell them that I didn't make you learn it. Okay?
Professor is better than you.
Throw it on me. I will defend you to the death. Okay. We have to find the parent structure of CO2. Okay? First thing is Lewis structure, right? Anybody really did CO2? Does anybody remember what it looks like?
The oxygen had a double bond, one of them did.
Yeah, there's actually 2 double bonds. It looks like that. Okay? So with our parent structure, we're always concerned about the center atom. How many things are on our center atom? 2. So what is our parent structure called? Linear. Yeah.
So like double bonds don't matter
No.
at all.
A double bond counts as one thing. A triple bond counts as one thing.
So how do we draw that?
In shape, you see,
Is that how we have to draw it? Just do that and then say it's a linear?
we'll get there.
Okay.
We'll get there.
So
No.
we're looking at the bonds around the center structure
Yeah.
to tell the parent structure?
Not just bonds, but things. Because
Okay.
if you had a lone pair here, that would be 3 things.
Okay.
Okay? But that's not that. So there are 2 things. If you have 2 things, the parent structure is linear and your bond angle is what?
180.
180. That one's easy to remember, right? Let's go to our SO2. SO2 was this weird one where we had a double bond on one side and a single bond on the other, and then there was a lone pair up there. Okay? How many things are on our sulfur?
3.
3. A single bond, a double bond, and a lone pair, but they all count the same. So that's 3 things. So what is the parent structure called? Trigonal planar, and our bond angles are
120.
120. Okay? And then there is water. So that is OH, 1, 2, 3, 4, 5, 6, 7, 8. That's the Lewis structure for water. How many things are on our oxygen? 4. So what's our parent structure? Tetrahedral. What's the bond angle?
Less than 1.5.
109.5. Okay? 109.5. Don't make it any harder than that. So we've named our parent structure. That is only the first step. Okay? Parent structure is not the shape. The shape only includes the atoms, not the lone pairs. So what you have to do is you have to imagine this in 3 dimensions, and then imagine that you have balls where the atoms are, and then nothing where the lone pair electrons are. So here is our water, okay? Here's our 4 things. Do you see the parent structure here? Tetrahedral with the one going up, and then the pyramid underneath, okay? But when we draw the shape, we don't draw the lone pairs. So the shape is just that. It's just that part of it. Yeah.
Okay, so there actually are like extra electrons just in the shape. Because they're not like.
Yeah, so so the Lewis dot, we're concerned about the electrons. In the shape, what we're concerned about is if we could see atoms, what it would look like. And you assume you can see atoms, but you can't see electrons. Okay? So if you look at this, all you see is you see atom, atom, atom in a triangle shape. I almost forgot the word again. So that is your shape of this. Okay. So here is our put CO2 back up here. Here's CO2, there's SO2. Why do they have different shapes?
Lone pair.
Uneven amount of electrons.
Right. So this one, this parent structure is linear, right? But there are no lone pairs, so you see everything, right? So you have, if you draw the parent structure, it would be, it would look like that, but there are no lone pairs to ignore, so the molecular structure, the shape, also looks like that. Okay? What is the parent structure of the SO2? Trigonal planar. So if we put our S here, we have oxygen, oxygen, lone pair. There's our 3 things, right? In our shape, we erase the lone pair, and so we're left with this, what we call bent shape. Which is why, even though both CO2 and SO2 have a center atom and 2 oxygens, CO2 is straight, it's linear, and SO2 is bent. It's all because these lone pairs repel these bonds and make them go down. Yeah.
Is there a way to distinguish the trigonal planars from the tetrahedral when they're like lone pairs? 'Cause like they look
I would
exactly
think
the
that
same.
would
When you draw it.
So like you draw it, they look exactly the same.
The bent, I mean, so that,
So, like,
so
H2O.
that bent versus that bent?
Yeah.
What would
What's
be
the
the
angle?
bond angle here?
195.
What would
Also,
be
it'd
the
be
bond angle
closer.
here?
120.
120.
So you have to know like the bond.
So you'd have to, yeah. So on an exam or something, if this would be, I think there's a table with the names, all the shapes we'll go through. I think this is called bent, and that is called bent, but they have different bond angles. So you'd have to differentiate by saying which bond angle it has, 120 or 109.5. And that just comes from the parent structure that you went through to get to your shape. So that is just what we did. Make your Lewis. Figure out your parent structure. Draw your parent structure and erase the lone pairs. Okay. if you can skip that step, if you can picture it in your head and say, this is what it's going to look like, and if I take away those lone pairs, this is what it's going to look like now, good for you. Okay? If you can't, draw the whole thing and erase your lone pairs. Okay. So here's a table. This may or may not help you. I think it's 2 or 3 slides long. Okay? It's every combination of parent structure and number of lone pairs. Okay? So if you have linear, you're always going to have both of your things are going to be atoms. Okay? They're going to be bonds. You won't have something that's linear that has 1 bond and a lone pair. That just wouldn't happen. Okay? So if you have 2 things, say A is our center atom, then X's are our things on the outside. So if you have something that is in this parent structure, linear, your shape is going to be linear. There's no other way around it. Okay? If you have an A and then 3 things around it, you have three things, and all of them are atoms. Okay? Your parent structure is what? Trigonal planar, and since they are all atoms, your shape is the same as your parent structure. So your shape is trigonal planar. But if one of them is a lone pair, you look like that, you erase your electrons, and you just get that bent shape. Does everybody see that? Yeah.
So as long as you're focused on number of things rather than number of bonded atoms, then you're
Right.
safe.
If you focus on things to get the parent structure, and then you focus on the atoms to get the shape. If you have 4 things, you're tetrahedral. Okay? If all 4 of them are atoms, then your shape is tetrahedral also. Okay? If one of them is a lone pair, you end up with just the pyramid part, not the little spike coming out the top. Okay? And that is called trigonal pyramidal. Okay? It's kind of like a triangle. It's got 3 things with trigonal, and it looks like a pyramid. I would just remember it. Yeah.
So since it's 3-dimensional, it wouldn't matter which 2 you erased. So like
Nope.
the AX2.
So
it's
if-
the same.
If we go back, if we go back to this, if I take away that one, it looks like that, right? If I take away this one, I can turn it, and now it looks like that. It's the same. If I take away this one, I can turn it like that, and if my marshmallows are where they should be, they should all be pointing down. It would be kind of like that. Okay. It doesn't matter which one you take away. You're still going to end up with that shape. Okay. If 2 of them are lone pairs, you start with that. It looks like that. You ignore, just erase the lone pairs, and what you're left with is another bent molecule. Like you were talking about before, this bent is different than that bent, because this is 120 degrees, and this one is 109.5.
What do you mean by lone pair? Like just,
So the lone pairs are these
Okay, so-
electrons that are on an atom, but
Mhm.
not part of a bond. That's
okay.
called a lone pair.
Would it be a mistake writing the angle? Should we write trigonal pyramidal?
If the question does not ask you for an angle, you don't have to write it. If the question asks you for an angle, write it. Okay? Yeah.
What's the angle for trigonal pyramid?
So, the angle is just determined on the parent structure. Okay? So everything here has 109.5. Okay? Yeah.
We didn't know like each individual shape name.
Yes. it's fair game to ask you a shape, and it can be any of these.
But you would like show like the pair. Like you would show the
So in,
non-bonded pair.
so if you had a question that said, draw the molecular shape of SO2, okay? You would have to do the Lewis structure, draw it, erase your lone pair. There should not be lone pairs in your shape drawing, okay? They just shouldn't be there, okay? You want to use lines to just sticks to hold things together in a shape, okay?
So that would just be bent.
This would
The
be
SO2 be bent.
bent. And if the question asks you to label the bond angle,
So whereas like the H2O would be trigonal pyramidal, it would look like the same shape. Or it'd be bent.
H2O is bent also. It started as tetrahedral, because there were two lone pairs on here. But we erased them to be left as that. And so we have a bond angle of 109.5. And here we have 120 degrees. But they're both bent. But they're both called bent. It's not bent and more bent. They're both bent, and then you have to give the bond angle. Okay. But if the question just said, what is the name of the molecular shape, you could say bent for either of them, and it would be correct. If it just says name, but it would probably say name and angle. Okay. So here's an example. What is the shape of the nitrite ion and what is the angle? So we have NO2 minus, how many electrons do we have? Two oxygens is 12, plus 5 is 17, plus 1 is 18. Don't forget the one that comes from the negative, okay? If you add it up and you have an odd number, that means you're going to have an electron by itself, and that can't happen, right? So you know you did something wrong. So here's our N, O, O. We have 18 electrons. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is that right?
No. Nitrogen needs 2 more bonds.
Okay. So what do I do?
So one of them has to, like the oxygen, move 2 over.
Yeah, so I'll move these over here, so we end up with N, O, O, single bond, double bond. Brackets too. Yeah, thank you. Minus, okay. That's our Lewis structure, okay? So how many things are on our central atom? 3, which makes the parent structure what? Trigonal planar, okay? So, the way I would do it is start with trigonal planar. I got 2 oxygens and a lone pair.
Would you
Okay.
erase the lone pair though?
And then come back, erase the lone pair, and you're left with what shape? Bent. And they ask, what is the bond angle? 120, because this bent came from trigonal planar, right? Yeah.
Why doesn't up there? Why doesn't it show it as like bent? Like on a test, would it show it bent like that?
No, 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 it would not. It doesn't show it there because it's text and can't do that. But no, it would not, because that'd be giving you the answer basically. So they're going to give it to you in linear form and make you figure it out. Okay. There are the steps if you need to go through it later. can be polar molecules also. We talked about polar bonds, right? Polar covalent, non-polar covalent. There can also be polar molecules and non-polar molecules, okay? And this just has to do with visually
Wait, I have a
picturing.
question about that, just before you erase it. Is that supposed to be a double bond? Like, do we show it as a double bond when we draw the structure?
Or slide over.
Yeah.
Trying to decide what to tell you.
I just
If-
saw it
if-
slide
If I tell you to make it a double bond, then we have to. Okay, maybe it's not, isn't it? Tell me if this is tricky, okay? If you have a double bond, you put 2 lines. Single bond is 1 line, double bond is 2 lines, triple bond is 3 lines. Okay? Does that seem straightforward enough?
So technically that's supposed to have 2 bonds on it, because it has a double bond on one side?
Yeah. So, if you were drawing the chemical structure, to me, there's a difference between a chemical structure and a molecular shape. In a chemical structure, yes, you have to say that. But in my head, the shape, you don't care about what the bonds are. Okay? But if you do this, you're definitely not going to be wrong. Okay? And I know I would not have to defend you on a final exam if you did that. If you did it the other way, with just a single bond, I would defend you, but I would have to defend you, possibly. I don't know what the other professors think. Okay. Does that confuse everyone?
No.
Okay. So, our polarity of our molecules, we start by looking at the bond polarity. Okay? What makes a bond polar? Talked about this. Unequal attraction. And if they have unequal attraction, what do we call that attraction? Electronegativity. Electronegativity is the attraction, the strength at which it pulls on an electron. Okay? So the bond is polar if you have the 2 atoms are not the same element, right? And they're not carbon hydrogen. Okay? In a diatomic molecule, if we have, say we have O and O, the polarity of the molecule itself is just the polarity of the bond, right? If this bond is nonpolar, the whole thing is nonpolar. If this bond, let's say we have an N and an O, and we have that. This oxygen is more electronegative, right? So it's going to have partial negative, partial positive on the nitrogen. It all comes from that one bond, okay? So a diatomic molecule is easy. Look at the polarity of the bond, and that's the polarity of the molecule. Where it gets harder is when you get into polyatomic molecules, okay? So a nonpolar molecule is either going to have all nonpolar bonds, or where this is going to make your head spin for the next hour, trying to figure this out, you can have polar bonds that cancel each other out, okay? Well, last semester, students really had a hard time visualizing this, okay? So let's go back to, I guess nothing I have drawn up here is a good example. There will be examples up here. If you have equal polarities, but they're in opposite directions, they're going to cancel out. Okay? So let's imagine, here we have N, O, and O. Okay? Say the polarity of this bond is same as the polarity of this bond. But this one has partial negative here, this one is partial negative here. Those two cancel each other out, and so the whole thing is non-polar. Okay? So this oxygen is wanting to pull the electrons over here, this direction. This oxygen wants to pull these electrons this way, and in the end, nothing happens, okay? It's like a tug of war where both ends are pulling with the same strength. What's in the middle, the electrons, don't go anywhere. So your whole molecule doesn't have a polarity to it. A polar molecule has to have polar bonds. If you don't have at least one polar bond, your molecule will not be polar, and they cannot cancel out. Okay? So, here is a molecule, and there is a molecule. Which one is polar? Why?
Because they
Shape.
have unequal attractions too.
So, to me, I look at this one, and they both have polar bonds, right? Because that element is not the same as the white one, because of different color, and that element is different than that element. So they both have polar bonds. Then this one, they cancel each other out though, because it's a linear. Those two polar bonds are opposite each other. In this one, they don't cancel out, okay? If you can draw a line through that atom, and so what's on the left and the right, or the top and the bottom, are not the same, they don't cancel out, okay? So on this one, if I draw a line there, it's the same on the both sides, right? If I draw a line here, it's the same on both sides, right? So that one cancels. This one, if I draw a line here, is it the same on the top and the bottom? Yes, it is, in this direction. But if I draw the line here, is it the same on the left and the right?
No.
No. So they don't cancel out. So what's going to happen here is you have, I think this is SO2, so let's just,
Looks like H2O.
is it H2O?
Yeah, they didn't use the oxygen like hydrogen.
Okay. Good catch. So let's go oxygen, hydrogen, hydrogen. Time to go home. Okay. So what happens is you have this negative pulling that way and a negative pulling that way. Okay? If you've taken physics and you've done vectors, it's probably a whole lot easier for you. I don't know how many of you have done vectors. Okay? But you see how the up, this one kind of goes partially up, this one kind of goes partially down, right? The up from that one cancels down from that one, which is why if we draw a line there, it's symmetrical. But both of them are going left. So there's nothing to cancel out going that way. So it's, you have this net polarity at the end. The oxygen has a partial negative, and both of these have partial positive, like it shows. Okay. The trick is picturing it in 3 dimensions and figuring out if the bonds cancel. Okay, that's the hardest part. So here is SO3. Okay. So are the bonds in SO3 polar or nonpolar? They're polar just because they're not the same element. They're not the same element, so automatically they are polar. But that is symmetrical, okay? It's like it's like that. I can draw a line right through here, and it's symmetrical, okay? If you're able to think about it in terms of forces, This one is canceled out half by that one and half by that one, because it's right in the middle of them. Okay? Otherwise, you can look at it and say, well, that's symmetrical, right? A triangle like that is symmetrical, so they all cancel out.
So if you were to try to slice it, it would be by the plane of,
So when you slice this, you would have to go right down the middle of one of the oxygens. So each side has an oxygen, a whole oxygen, and then half of an
so
oxygen.
it could necessarily, or it could be split on a trigonal plane or a tetrahedral.
Yes. The trigonal planar is easier to visualize. Because this one, you can easily imagine drawing that line and splitting it, right? The trigonal planar is really hard to draw that line, because it's in 3 dimensions. I can't draw a 3-dimensional line with a laser pointer, right? So you have to realize that I can turn this any way I want. And it's going to look the same, okay? It's symmetrical in a 3-dimensional fashion. So, in this case, since all of them are chlorines, all of the bonds are equally polar, and when you take all 4 of them together, they cancel out. Okay? That is probably the hardest one to visualize. You agree? You just have to take it for granted that if you have all 4 of them, and they're all the same, they cancel out. What would happen if you removed this top chlorine? Would it be symmetrical then? No. Because then I can draw a line like this, and I have 3 chlorines on the bottom and none on the top.
In
Okay?
order to be symmetrical, do you have to be able to draw a line from every direction, like, in a even?
No, because I'll say on this one I could draw a line like that,
Okay.
and that's not symmetrical. That's not, it's not a mirror image top and bottom, but that molecule is symmetrical because there is a line that you can do it. Yeah.
It might just be easiest to say you can draw any line along the bond as it's going with the particle.
Yes, you could say that. So when you draw a line, it has to go through a bond. You could say that. If any of you, this may not help or this may confuse you. If any of you have ever used a centrifuge, who's used a centrifuge? Okay. Have you ever put 3 things in a centrifuge? If you put them in a triangle, wow. You put them in a triangle shape, the centrifuge is actually balanced, right? That's really the only situation that you can do that with an odd number, otherwise you have to have them opposite each other. But you can balance with 3 things.
What polars? That says polar bonds. I thought non-polar bonds.
So in these cases, the polar bonds that they have cancel out.
Oh,
Okay. So this is our CCl4 with one of them replaced with a hydrogen. Is that polar or non-polar? Polar. You have 3 chlorines on the bottom, 1 hydrogen on the top. Is that polar or non-polar?
Polar.
Polar. All of a sudden, you can arrange it so you have a chlorine sticking one way and 3 hydrogens sticking the other way. Is that polar or non-polar?
Polar.
Polar. You can arrange it so that 2 chlorines are sticking one way, 2 hydrogens are sticking the other. Okay? Polar, non-polar?
Polar.
Polar. Polar, non-polar?
Polar.
Polar. Polar or non-polar?
Polar.
Polar. It's important to notice these green ones are not going straight out. They're angled slightly down, right? So if I draw a line like that, then all the chlorines are on the bottom and there's nothing on top. Polar or non-polar?
Non-polar.
Non-polar. They're polar bonds, but they're in that triangle shape. They're in a triangle shape and they cancel each other out. Okay? So, if you were going to, we're gonna stop here, okay? But you're still responsible for this, okay? If you were asked this question, polar or non-polar, you have to go through the entire process. Lewis structure, the parent structure, to shape. Get your shape, and then figure out, is it symmetrical? Okay? That is how you would do that. Okay? If anyone wants to go through these, we can do it after class. I just don't want to hold people up. Okay? It's been a long class. Okay. And the last, just very quick concept, like dissolves like. Okay? Things that are polar will dissolve in liquids that are polar. Things that are non-polar will dissolve in things that are non-polar. Which is why salt, which is polar, it's ionic, it's very polar, will dissolve in water, which is polar. But that's why vegetable oil, which is non-polar, won't dissolve in water.
What about like canola oil and vegetable oil?
Well, if it's an oil, it's non-polar.
They'll
Okay,
mix together?
right. And so the magic of soap is soap has a polar end and a non-polar end. So that's why everything, soap and oil and fat and stuff, are soluble in soapy water. Okay. Okay. Well, we're not going to do this. If you want to go through it, be my guest.
No.
Okay. It's just, we can do it very quickly, but not online. You have to make a solution of cholesterol. That is cholesterol. Would you use water, ethanol, which is that, or octanol, which is that? What do you think? Does that look polar or non-polar to you? It's basically all carbon, right? It's slightly polar, there's a little oxygen here, but that little bit of polarity is overwhelmed by this huge thing that's non-polar.
So
If
it'd be
it's
not
carbon
polar
bonded
by
to
default?
carbon, it's completely non-polar over here. So cholesterol is basically non-polar. So you would put it in the most non-polar solution solvent that you have, which is octanol. Okay? Because again, like this, there's an OH down here, but then a whole bunch of carbons. Yeah.
So like the higher the ratio, the more polar it is.
The more carbons you have, the less polar you are. Does that make sense? So if you had a whole bunch of oxygens, then it would be more polar. Because you have more polar bonds.
So the one on the bottom is just more polar than the one on the left.
No. This has,
With more carbons.
right, they both have one OH, but this has 8 carbons, this one has
The
2.
one on the left is the most polar.
Of these two, yes. I didn't draw water, but water is one of the other options. Water is the most polar, and then ethanol, and then
Okay. So carbon is more polar.
yes. Okay. Last thing is quiz. Okay. So if you will clear your desk.